Good morning, students. I am here today with the leftover topics of electric potential. In the previous lecture, we had discussed potential at a point due to a point charge and a system of point charges. Now, we shall learn how can we find potential at a point due to an electric dipole. So the heading is electric potential at a point due to an electric dipole. In order to find electric potential due to an electric dipole, three cases may arise. Three cases. And all the three cases I have written on this board. Case number one, at a point on the axial line of the dipole. It means the point should lie on the axis of the dipole. Second one, at a point on the equatorial line of the dipole. It means point should lie on the right bisector of the dipole. And the third case is the general case, that at a general point due to a dipole. It means point lies neither on the axial line of dipole nor its equatorial line. It may lie anywhere from the dipole. We shall discuss one by one all the three situations. Let us take the first case. Electric potential at an axial point of an electric dipole. Students, see over here, I have taken a short dipole, AB. AB is a dipole which consists of two charges, minus Q and plus Q, separated by a small distance 2L. So 2L is the distance between both the charges. And this dipole is placed in vacuum. On the axis of dipole, this positive x-axis, I have taken a point P. P is the point on the axis of dipole at a distance r from the center of dipole. And you are supposed to calculate electric potential at point P due to this dipole. So, in order to calculate electric potential at point P, what shall we do? It is said that we will calculate electric potential at point P due to minus Q charge, then electric potential at point P due to plus Q charge, and when both the potentials are being added up. And that will give the value of total potential at point P due to this dipole AB. So from figure here I have taken a notation. AB is equal to 12 and O is the midpoint of dipole. So O to A and O to B is L. OA is equal to OB is equal to L. And O to P is R. So OP is equal to R. We shall use the notation where it is required. So let us find the potential at point A due to minus Q charge first. So here potential at point P due to minus Q charge. Suppose it is V1. So it is Q by 4 pi epsilon naught minus Q, and at the place of distance AP, A to P, AP. It becomes, take minus here, 1 by 4 pi epsilon naught Q, and AP is R plus L. R is here and this distance L. So AP is equal to R plus L. First equation. It gives the potential at P due to minus Q charge. Similarly, potential at P due to plus Q charge. Here, potential at P due to plus Q charge. Take, suppose it is V2 is equal to 1 by 4 pi epsilon naught Q plus Q. This one Q and distance BP. So it becomes 1 by 4 pi epsilon naught Q and BP is R minus this distance, R minus L. This is the question number 2. So equation 2 gives the potential at point P due to plus Q charge. So what is the potential at P due to this dipole? Add both the equations. It means V1 and V2 will be added up. This will give the potential at P due to this dipole. So here potential at P due to the dipole, Vp is equal to V1 plus V2. Put the values of V1, V2. V1 is this over here minus 1 by 4 pi epsilon naught Q by R plus L. V2 is this plus 1 by 4 pi epsilon naught Q by R minus L, and solve it this equation here. So Vp is equal to take Q and 1 by 4 pi epsilon naught common, Q by 4 pi epsilon naught 1 by R minus L minus 1 by R plus L, and solve it. So in bracket R minus L and R plus L, take the LCM, Rx square minus L square, and here in numerator R plus L minus R minus L, and after solving this we will get 1 by 4 pi epsilon naught, Q is here, and this term becomes 2L. So Q into 2L and denominator R square minus L square. Students, we know the word dipole moment. Dipole moment is the product of charge and the distance between both the charges. So Q and 2L. 2L is distance between both the charges. So Q into 2L is the dipole moment. So equation will be Vp is equal to 1 by 4 pi epsilon naught. P is this one. Q into 2L. P by R square minus L square. Here I have written P is equal to 2QL, and this is called dipole moment. Now one case also we can take. This dipole is suppose very short. Very short means this distance R is much greater than this L. So what will happen? Here I have written that. Note, for the short dipole, R square is much greater than L square. And in this situation, this L will be negligible, it can be neglected. So L square you can take tends to 0. So what the equation becomes? In case of the short dipole, this equation becomes Vp is equal to 1 by 4 pi epsilon naught P by this R square, and L square will be neglected. So this equation gives the potential at point P due to a short dipole. So these are the required expressions for the potential at P due to the short dipole on the axial line. Now we'll see the next case. Now we shall see the second case, that is electric potential at an equatorial point of the dipole. And here is the figure. See, I have taken AB is a short dipole consisting of two charges, minus Q and plus Q, separated by a small distance 2L, is placed in vacuum. P is the point at perpendicular distance from the midpoint O of the dipole, and at this point P, the electric potential is supposed to be calculated. Here, following the figure, if O is the midpoint of dipole, so AB is if 2L, O to A and O to B will be L and L. Now OP is R and AP and BP both are R square plus L square under root, because this is base is L perpendicular to R, and hypotenuse becomes under root R square plus L square. Now, in order to find electric potential at point P on the equatorial line of this dipole, due to this dipole, what shall we do? Like the previous case, we shall calculate potential at P due to minus Q charge, then potential at P due to plus Q charge, and after this we shall add both the potentials. This potential will give the value of potential at P due to this dipole. So first case, electric potential at P due to minus Q charge, this one. Suppose it is V1, 1 by 4 pi epsilon naught minus Q by this distance from the charge to that point, AP, and this is equal to, take the minus out here, 1 by 4 pi epsilon naught Q by AP is equal to under root R square plus L square. Equation number 1. And again, potential at P due to this plus Q charge, potential at P due to plus Q charge, suppose it is V2, 1 by 4 pi epsilon naught plus Q by this distance BP from the charge to the point BP, and BP also equal to R square plus L square. So 1 by 4 pi epsilon naught Q by R square L square under equation number 2. Question number 2. So then the total potential at point P due to this dipole at P due to this dipole will be summation of both the potentials V1 and V2. So here for electric potential at point P due to dipole, Vp is equal to V1 plus V2. Now put the values of V1 and V2. V1 is here and V2 is here. So V1 is minus 1 by 4 epsilon naught Q by under root R square by L square, and plus V2 is here 1 by 4 epsilon naught Q by R square plus L square. Both the values are the same. One is positive, other is negative. So they will cancel out and the total potential Vp is equal to 0. So that's why you can say the potential at point P due to dipole will be 0. So here written potential due to a dipole on its equatorial line is 0. Now we shall see the third case. Let us see the third case. Third case is potential at any general point due to a dipole. To find the potential at a general point, I have shown here one diagram. I have taken AB is a short dipole which consists of two charges, minus Q and plus Q, separated by a small distance 2a. 2a is distance between minus Q and plus Q. O is the midpoint of the dipole. And from midpoint O at a distance r, there is a point P at which electric potential due to this dipole is required. It means you have to find a potential at point P due to this dipole. And this point P lies at a distance r from midpoint of the dipole. This point does not lie on the axis of the dipole. This point does not lie on the equator of the dipole. It lies anywhere. So that is called the general situation. In order to find a potential, I have done some geometrical and mathematical treatment. We know the dipole moment. Dipole moment is always directed from negative charge to the positive charge. So here vector P represents the dipole moment. And assume I have taken this dipole moment makes an angle theta with line OP. I have written over here. Let dipole moment P makes an angle theta with the line OP. Number 1. Number 2, in order to find potential, formula is here. V is equal to K Q by R, and R is the distance from that point to the charge. But here charges are at point A and at point B, and distance are given from point O to point this R. That's why you have to join both the lines from point to charge minus Q, from point to charge plus Q. So we'll join AP and BP and assume AP is equal to R1 and BP is equal to R2. Here I have written. According to figure, OP is equal to R, O2P is equal to R, AP is equal to R1 and BP is equal to R2. Now one thing more I have done, that I have just increased this line PO to the point C, and I have dropped two perpendiculars. One perpendicular AC on PO produce, another BD on PU. Why? Because we have got two triangles, and in these triangles we will get the value of OC and OD. It will help in the calculation of the potential. So in triangle AOC, here written triangle AOC, OC is equal to L cos theta. Why? Because OC is equal to L cos theta. This is the angle, this becomes the hypotenuse. This becomes the hypotenuse, L is the hypotenuse and OC is the base. So OC is equal to L cos theta. In the triangle ODB, in this triangle or BOD we can say, again OD is equal to L cos theta, because this is your hypotenuse and OD is the base. So this will help in calculation of the potential. Now, in order to find potential at point P, we shall calculate potential at P due to minus Q charge, potential P due to the plus Q charge. Here I have taken V1 is potential at P due to minus Q charge, V2 potential at P due to plus Q charge, and when both will be added, it will give the value of potential at P due to this dipole. So V1 potential at P due to minus Q charge 1 by 4 pi epsilon naught minus Q by this distance AP. V2 1 by 4 pi epsilon naught Q by this distance BP. Now put the value of AP and BP. Take Q by 4 pi epsilon naught common. So 1 by BP, this minus will hit this side, is minus 1 by AP. So BP is R2 and AP is R1. So potential at point P, this Vp becomes Q by 4 pi epsilon naught 1 by R2 minus 1 by R1. This equation 1 gives the potential at P due to this dipole AB, but in terms of R1 and R2. Here the question is given in terms of R we have to find. So we will have to calculate this R1 and R2, or we have to convert this R1 and R2 in R. How shall we convert? Students, we know that this dipole is very small. So dipole is very small. So distance AO and distance OB will be very small distances. And AO and OB are small distances. So points A, B, C and D all will be very close to each other. As a result, what the value of this R1? See here, written R1 is equal to AP, R1 is AP, and AP I have written nearly equal to CP, P to C, CP. Why? Because point A and point C is very close to each other with O, with respect to O. So CP is equal to what? CP is equal to OP plus OC, OP plus OC, and put the value as OP and OC. OP is R, here we have OP is R, and OC is L cos theta, here we have OC is L cos theta. Similarly R2 is how much? BP. R2 is BP, and this BP will nearly equal to DP, because point D is very close to point B with respect to O. So DP is equal to what? DP is equal to OP minus OD. DP, this one, is equal to O to P minus O to D. Now OP minus OD, put the value of P is R, OD is again L cos theta here, OD is L cos theta. So this is set of equation suppose 2. Now we shall put the value of this set of equation 2 means value of R1 and R2 in equation number 1. Here R2 this value, here R1 this value, and we shall get the result. So equation becomes Vp is here, Q by 4 pi epsilon naught is here, and 1 by, at the place of R2 we shall write R minus L cos theta minus 1 by R1. At the place of R1 we shall write this R plus L cos theta. And we solve this. Q by 4 pi epsilon naught is common, and denominator L square L square R square minus L square cos square theta is the LCM, and numerator becomes 2L cos theta. Second step, multiply this Q with 2L, so becomes 2QL cos theta. This 2QL cos theta, and what is this 2QL? 2QL is dipole moment denoted by capital P. So here and down, P at the place of here we write the BP, and here 1 by 4 pi epsilon naught. 2QL is P, dipole moment, cos theta as it is, and here R square minus L square cos square theta. So this expression gives the value of electric potential at point P due to this dipole at any point. Theta is angle inclined, this line OP is inclined at angle theta with the dipole moment. Now you can check this equation correct or not. For the case of axial line, you can put theta is equal to 0 degree. You check the result with the axial line. In case of equatorial line, you put the theta is equal to 90 degree and check with the equatorial line. It means this expression gives the value of electric potential at any general point P due to a dipole. Now we shall see some sample numerical. See one sample numerical which will help you in solving numerical further. I have taken one very simple numerical. An ammonium molecule has permanent dipole moment. Value is given 1.47 dy, and 1 device is equal to 3.34 10 power minus 30 coulometer. Then calculate electric potential due to this molecule at a point 52 nanometer along the axis of the dipole. Assume potential at infinity is 0. Means along the axis of dipole means we shall apply the formula for the axial line. So first of all we shall write what are given data in the numerical. So dipole moment is given 1.47 divide. This is equal to 1.47 into this value 3.34 10 power minus 30 coulometer. So dipole moment is this coulometer. And distance 52 nanometer. R is equal to 52 nanometer. Nanometer means 10 to the power minus 9. So 52 into 10 to the power minus 9 meter. Then question is potential on the axial axis of dipole means V axial is equal to what? Students, we have derived in the theory part the potential at axial line for short dipole is this. V is equal to 1 by 4 pi epsilon naught P by R square. This is for the short dipole. And for the short dipole, this R is much greater than L. So we shall put the values over here. Now for this 1 by 4 epsilon naught 9 into 10 power 9. P is here whole all out 1.47 3 point into 3.34 10 power minus 30, and R is this one 32 into minus 9 square. And when you solve this, we will get the result 1.63 into 10 power minus 5 volt. This is the answer of the dipole for the ammonium molecule along the axial line. So similar manner you can solve the numericals for the equatorial line or other numerical given in the NCERT as well as given in the assignment. Please solve. So thank you so much. Now we shall see the next class. We shall meet with the next class with the next topic.